All right, so let's go ahead and take a look now at section 1.3, diffusion through a cylindrical wall. So our application here is for the purification of gases. And one of the purification processes that is proposed for natural gas that has helium in it is to separate the helium out from the natural gas by diffusing it through Pyrex tubing. And the reason Pyrex tubing is thought to be a possibility is because it has an anomalously high diffusion rate for helium, about 25 times that of even hydrogen. And so we're going to go ahead and take a look and analyze this problem and see if this is a good possibility for a method of separating helium from natural gas. And the idea would be to use an array of tubes so that the more surfaces you have, right, the more helium, more throughput, the more helium that could be extracted. And so all of this helium here would be collected as it comes out of these tubes. And then, of course, the natural gas is also collected that comes out this end of the tubes. All right, so we're going to go ahead and calculate the rate of helium extraction in a small tube array apparatus. And in the end, we're going to look at the rate in cubic meters of helium that is separated at standard temperature and pressure per hour. And so these are some of the parameters, and you can look through those on your own, but we'll go ahead and use those at the end. So we want to go ahead and use our control volume method to figure out our governing equations so we can get the flux that's moving through these walls. And so again, we're going to look at this cylindrical case for the tubing. Since we're doing a cylindrical case, our control volume is going to be different now, right? In the rectangular system, 1D, we were looking at a cube of volume. Now we still have a one-dimensional problem in that we're diffusing in the R direction, right? This is a cross-section of the tube. But now our control volume is going to be a cylindrical shell. So this blue region in here is just meant to represent the control volume, and then it goes in and out of the board. And so it's a very thin cylinder, so cylindrical shell. The location of this control volume is just at some position R. And as we go through it, we would let R go from R inner to R outer. So this control volume will shift as we look at this problem. And so our inner and our outer will be our boundary conditions. And so at this surface, we'll have a concentration CI that's fixed, and on the outer surface, we'll have a concentration CO that is fixed. So those will come back at our boundary conditions. If we go ahead and pull this cylindrical shell out, just to look at it in a little more detail, this shell inner surface we can say is at position R. And just like we did in a rectangular system, the other surface is at a position R plus delta R, right? Before it was X plus delta X. And so in the end, what we're going to do is let this delta R become very thin. And so this becomes a very, very thin cylindrical shell. All right, but we have this surface here that we're going to diffuse through, and then into the control volume, and then this outer surface here, we're going to diffuse out of the control volume. So remember, before we had the mass balance, and remember this term here is in kilograms per second, right? This is a kilogram per volume times volume, so that's just kilograms, and then times seconds, so kilogram per second term. And we needed a flux times an area. So we're going to have the same thing now, it's just that now we're moving in the R direction. So we're going to refer to our flux then as J sub R. And it's moving through an area. The area, the surface area of the cylindrical shell that it's moving through is given by 2 pi R times L. And that's evaluated at position R, the inner surface, and then at position R plus delta R, the outer surface. Okay. And this volume term is given by 2 pi R L delta R. Okay. So the area term hopefully makes sense. This is just the surface area of a cylinder. right? And it's just located at 2 positions. So the inner surface, this R value is going to be different than the R in here, which is going to be an R plus delta R position. All right. So we have to keep the R's in here when we're doing the evaluation in our next step, and we write this as a differential equation. But the 2 pi and L are constants, so we could pull those out. The volume term, this might not be as obvious, because you might be thinking of a volume term that might be something like a pi r squared times L for the outer, and then subtract off a pi r squared L times the inner. So we'll talk about this in class, where this comes from, but this is true in the limit when delta R becomes small relative to our position R. So again, this is an approximation that's true in that limit, and we'll talk about that in class. So if we go ahead and divide through by the volume, you can see the 2 pi and the L's are going to cancel out of these terms. We're still going to have the R delta R left from the volume, so that's here. And we still have the R that's inside of our evaluations. So we can't pull those out. Okay, so we have to keep them like that. And so now what we can do, if we were to take a look, if let's pull this R over here, so this is the 1 on R term, and then the remaining part, this function at R minus the function at R plus delta R over delta R, that again is the definition of a partial derivative, the negative definition of the partial derivative, and our function is j times R. So we've got the partial derivative of j times R dr, okay, just like we had before. And that is our continuity equation. Okay, so we got our continuity equation, and in the next video we'll go ahead and pick up here and we'll walk through our substituting in our constitutive equation, applying our steady state conditions, and then eventually solving this equation here. For homework, you're going to be looking at a spherical case. And so you're going to follow through a similar method as this, except you'd have a spherical shell in that case. And so our volume term is going to be different for a spherical shell, and so is the surface area for the spherical shell. And so we'll talk again about that also in class, and you can discuss that in groups, but we're going to need again another approximation for the spherical shell volume.